Okay, welcome back. So in this video I'll be talking about the different properties of waves. So in the last few videos I talked about the introduction to waves and the characteristics of waves. So in this video and the videos hereafter I'll be talking about the properties of waves. So what are the properties of waves? Now waves are very similar to the concept or the theory of light. Waves can be reflected, waves refracted, and diffraction and interference can also be done using waves. Now waves, now as I explained in the first video, is a single wave is actually a mode of energy transmission. So waves have various properties. So these properties of waves depend on the type of wave and the mode of energy transmission. Now you may have seen, as I explained in the last few videos, the transmission of energy in the case of a transverse wave is somewhat different from that of the longitudinal wave, and you can see that it is different for progressive waves and standing waves. So various waves have different types of modes, so actually modes of energy transmission. So the a single property, either reflection, refraction, diffraction or interference, depends on the type of the wave and the mode of energy transmission. So let's talk about these properties in detail. So when talking about the reflection, so as I mentioned, waves are somewhat similar to the actually the behavior of light and wave reflection is also similar to the concept as you describe the reflection of light. Now when we have some waves, so for example we have some sound wave like this, we have a source here, say for a loudspeaker or any other energy or audio transmitter here, we produce sound, so sound goes in this direction like this. So actually the reflection of waves as in light also obeys the laws of reflection. So one of the laws of reflection is that the angle of incidence, so the angle of incidence is like this. So the incident angle is the angle made with the normal by the source, and the reflected angle is the angle made by the reflected wave with the normal and is taken by the receiver. So if you have some sound source here, for example a loudspeaker or something, and if you have a receiver or a human ear, right, even your ear if you are accustomed, and you can hear that sound is reflected through this surface. You don't hear from here to here, right, from the source to the receiver, but the sound waves go here, reflect and come in. So you can measure the angle of incidence and the angle of reflection, and you can prove that these two angles are equal. So as in the case of light, reflection of any type of wave also obeys the laws of reflection. One of the other concepts that you need to understand is that now in the case of light, when some parallel beams actually meet a concave surface, right, a curved surface, in fact, they come to a focus. So that's about theory of light. So that is the reason as to why I explained to you at the beginning that waves behave in a similar way to that of light. So when you have a light beam here, parallel light beams, these beams converge to this point, right? So this actually we call the focus. So and in contrast, when you emit some light from the focus, now these waves, these light beams converge to this focus, and in contrast, when you produce some light from the focus, parallel beams are produced, right? Similarly, if you have the energy that is transmitted, or the wave that is transmitted from the loudspeaker or any other audio source, you can prove that these parallel beams of sound waves or the longitudinal waves converge to some point. So if you don't have to theoretically prove that, you can practically prove that if you have some curved mirror here and a loudspeaker here, when you increase the sound of the loudspeaker, at some point a higher intensity of sound can be heard. So that is the point of focus. Similarly, if you have a loudspeaker here, so this is actually now the second figure in which we have here the distribution of light through parallel beams, like beams or waves, when it is focused. So this is actually the concept of the loudspeaker. We have the focus here, and these sound waves get distributed, right, over the curved surface of the loudspeaker. So this is about the reflection of sound. So not only sound, various types of waves can be reflected. So I use the sound as an example. One of the other characteristics, or one of the other main properties of waves, is the concept of refraction. So you know that when some wave, refraction occurs when due to the difference of speed between different two medias, right? For example, if you have water and air interface, right? When some light source enters the water surface through this interface, what actually happens is that the relationship between the incident angle, the sine value of the incident angle, the ratio between the sine value of the incident angle and the sine value of the reflected angle is a constant for that medium. You can change the value of the incident angle, you can change the value of the incident angle, and according to the constant, that we call that the refractive index for such an interface. According to the refractive index, you get an appropriate reflected angle. So similarly, in the case of waves, when some wave meets an intersurface between two media, what actually happens is that this wave obeys the laws of refraction. For example, we'll use the same example of sound. Now sound, you can see now when taking two media, one in the air and the other in water, you can see that sound may propagate faster in the air, right? So when you go say inside some water source, for example the sea, the ocean, or the lake, or any other source, you can see that the sound takes a lot of time and the intensity is also low in water. So that actually depends upon the refractive index of the two surfaces. So this is another analogous situation in which we see the analogy between the light and the normal waves, the mechanical or the types of waves, in the concept of refraction. So this is what I was talking about so far. So we have an incident ray like this, we have an incident angle I, so this is the interface, and we produce a perpendicular here, this is the normal, so this is the normal which I call the interface, and according to the laws of reflection, the incident angle, the refracted ray, the incident ray, and the normal at the point of incidence all lie in the same plane, right? You can see that the incident ray is like this, reflected ray is so, and the normal, they lie in the same plane, and the sin I by the sin r is a constant. I is the angle of incidence and r is the angle of refraction, and we call this constant the refractive index, right? So that is about the refraction. Now, having explained to you that sound travels faster in air than in water, let's take another simple example in which sound plays a key role in identifying the properties of refraction in waves. One important example is that you can hear that sounds are easier to hear at night. So during daytime, you can see that if this is the ground level, so let's make a comparison here. During the daytime and nighttime, you can see that at the ground level, you can see ground level like this, and the upper layers of air are colder than the layers near the ground level. Now the ground level is hot and the upper layers are cold, right? And during the night time, upper layers are warm and the lower layers are cold. So sound travels, you know that sound travels faster when the temperature is increased. So I will explain to you about this phenomenon in another video, in some complex topics of waves in another video. So for now, understand that you can simply experience that practically as well. Sound travels faster at high temperatures. So what actually happens is that at the ground level, you can see during the daytime that the upper layers are cold and the lower layers are hot. So the sound converges out or away from the hot to the cold surface, right? So at the night, during the night time, the upper layers are warm and the lower layers are cold, so the sound waves converge towards the ground level. Now during the daytime, this sound waves diverge out of the ground level, and during the night time, sound waves converge, or they arrive, or they move towards the ground level. And another important effect of refraction can be seen of the effect of sound on the occurrence of wind, right? Effect of wind on sound. Now when the wind is blowing in the direction of sound, you can see that the bottom of the sound wavefront is moving more slowly than the upper part. Now this is the upper part, this is the lower part. What actually happens when the wind is flowing in this direction is that wind enhances the flow in some direction. So if the wind is moving in this direction, in the direction of the sound, right? In the direction of the sound is heard easily. So wind enhances the sound's propagation. However, when the wind is blowing away from the direction of the sound, now when the sound is moving in this direction and the wind is moving in this direction, so those two directions are not in the same direction, they are opposite in direction or some angular direction, the sound intensity enhances only in the direction of the sound.